so let's look at F2. So we're going to be making the MO diagram for F2, giving ourselves a lot of space here. So we got F, so this is our atomic orbitals that we're going to put in, and then we're going to make our MOs out of that. So when I do these, because I only like to use valence electrons, and so we're going to start off with the 2s because they are both the same atom. They are going to have the same energy on either side. I'm not going to do the 1s because it won't factor into anything that we'll be calculating or doing, so that's why. So down here, this is our sigma 2s, and up here is our sigma star 2s. I'm trying to save room for the p's, because we got a lot of stuff to put in. So this is the 2p, 1, 2, 3, and then over here, 1, 2, 3 for the 2p. Okay, I'm gonna do my little dashed lines here, and you'll see why that's more important when you have more of these going on. Okay, and so now we have 1, 2, 3, 4, 5, 6. We have 6 atomic orbitals in the p, so we have to make 6 in our molecular orbitals, and so we're going to have our first is going to be our sigma, so it's our sigma 2p. I'm not going to put the x, the y, the z for these. It's fine. They do come from the x, y, and the z, but it is beyond the scope of what we're going to use these for, so I'm not going to worry about it. And we next have the 2 degenerate pi orbitals. So this is our pi 2p orbitals. You know what? So this is, we're going to make these a little higher so that we can see that they're lower than our MOs are lower than our 2p. Okay. Let's do this over here. Got it. Okay, and then we have the other anti-bonding. So this is pi 2p anti-bonding, and then the sigma 2p anti-bonding. And so we can see that these are here, 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 and here. Okay. And then we're going to put in our electrons. So I'll do those in blue. So every fluorine is going to have, we have 2 and 1, 2, 3, 4, 5 in the P. That gives us a total of 7. 1, 2, 3, 4, 5. So the way that you're going to do this is you're just going to fill out. So the 2s is going to fill out completely. 4 electrons in the 2s atomic orbitals, and so we put 4 electrons in top and bottom. And now I'm just going to count all my 2p electrons. So I have 5 from one fluorine, 5 from the other. That's 10. So then I just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So you're going to fill out in the same way. And so once we have this molecular orbital energy diagram filled out, we can answer a bunch of questions. Okay, so we're going to go through all of them right now. The first thing I'm going to point out is we're going to give you a couple names. We're going to look at this is the highest occupied molecular orbital. So we abbreviate that HOMO. Okay, HOMO. And this is the lowest unoccupied molecular orbital. So that is a LUMO. So LUMO. Now this is really important because when we have molecules and they're being excited by light in the same way that we can excite an atom, of an element, then we're going to be taking electrons from the HOMO to the LUMO. So for example, if we have excitation, we're going to be taking an electron here and most likely moving up to here. So then this energy gap becomes an important to understand. What are the likelihood that we can excite a molecule? So knowing the HOMO and the LUMO are really important to knowing the delta E between the two, because we have much bigger differences if the energy is, if our HOMO is here and our LUMO is here, it can make a much bigger difference. Okay, rid of those, clean up a little bit. All right. Now, we have the HOMO and the LUMO. We also can calculate the bond order. So let's do that. So the bond order one half, and then number of electrons in bonding, that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8 minus, and then anti-bonding is 1, 2, 3, 4, 5, 6. So 8 minus 6 is equal to 2. 1 half of 2 is equal to 1. And that's what we expect. We see fluorine having this Lewis structure. So the Lewis structure, bond orders always match up with the molecular orbital bond orders. So it's a bond order of 1. Okay. And then we can simplify. Well, there's a couple other terms that we're going to talk about. We can either define this as paramagnetic or diamagnetic. Now, the reason why this is important is that unpaired electrons interact with the magnetic field because they don't have a spin of another paired electron to offset it. So once you have a spinning charge of any type, you create a magnetic field that's perpendicular to the movement of that charge, and that can interact with the magnetic field. So we can use this as identification. We can use it for lots of things. And so we only care if there is any unpaired electrons in our MO diagram. If there are, then it is paramagnetic. So paramagnetic means it is a substance with unpaired electrons that can interact with a magnetic field. Okay, so that's nice. And if we look at the diamagnetic, that would be where we have, in the case of fluorine, where every single electron is paired up with another electron. So that happens less often. So this is substance with no unpaired electrons. So we would say the bond order is 1. It is paramagnetic. And the last thing that we can do is that we can, to summarize, just like we summarize energy level diagrams for atomic orbitals or atoms, we can do the exact same electron configuration, but for molecules, it's almost the same with just one important difference. So we're going to do that down here. Let's see. Yeah, we'll do it down here. Okay. So what we're going to do is we're going to we're going to write out, instead of 1s and 2s, we're going to do, so sigma, sigma 2s. Now, there's 2 electrons in the sigma 2s right here, so then that would be 2. And then the reason why you put these parentheses, you'll see here, is for this reason, sigma 2s star squared. Because that star is already up in that exponent spot, we use the parentheses as a way to separate out those two. So, and then we have the sigma 2p, 2 of those, and then we have the pi 2p, pi 2p, and we have 4 electrons in the pi 2p, and then we have the pi 2p star, pi 2p star, and we have 4 electrons there. Okay, so that is a summary. This is the ground state configuration, or ground state. So we call this the, all right, this is the ground state electron configuration for F2. So I could ask you that, and you'd have to draw this diagram, and then what's the bond order? Will it interact with the magnetic field, or is it para or diamagnetic? And then what's the ground state electron configuration? You should be able to answer all of those questions. Okay. And then the last thing I want to show you is how to do, so these for, well, we can, let's just do another one real quick, and then I'll show you how to do it for an ion. There we go. So let's do atomic orbital, molecular orbital, atomic orbital. And we're going to do this for O2 2 minus oxygen, oxygen. Okay. So again, just doing 2s, 2p, 2s, and this is 2p. And so oxygen is going to have 6 electrons, 3, not 6. It's going to have, so, sorry, let's do oxygen has, let's get rid of these and let's do it in this order. Oxygen has, if we look at oxygen, it has 6 valence electrons, so it's 2, 1, 2, 3, 4. 1, 2, 3, 4. But because we're doing oxygen 2 minus, I have to add an additional electron to each. So this is looks like it actually should be for like a halogen, but it's actually for oxygen because we have a O2 minus. So you're going to account for the -2 in there, in the valence electrons, just like you would for like Lewis structures. And then we're going to put our sigma 2s bonding and sigma 2s star, and then we're going to do the sigma 2p and the pi 2p. Okay, now if you'll notice here, well, actually it is the same for oxygen here. Oxygen and fluorine both have their molecular orbitals for the lowest of the antibonding is pi. Now for nitrogen, it's actually flip-flop, where we actually have the sigma and the pi have switched. So don't be confused by that. I will always give you these basically I would give you this. I would not give you the number of valence electrons in the atomic orbitals, but I give you the diagram that you could then do all this to. And again, you can kind of see that this helps out a little bit when we're trying to show where these are coming from. And then we take our electrons and we're going to fill them in. So we got 1, 2, 3, 4, and now we have 5 on both sides. That's 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So hey, this actually looks a lot like fluorine. Okay, and you can see here that if that's the case, then the bond order, just like fluorine, bond order, we already calculated for fluorine, it's going to be equal to 1. So this is actually O, and this is 2 minus. So the stability has actually gone down because the bond order has gone down. If we look at what oxygen was like, so if we remove 2 of these to make oxygen, so if we get rid of 2, so remove to make O2, get rid of the -2 charge, then your bond order becomes, so for O2, the bond order is now, let's count it. So we got 2, so 2, 4, 6, 8, 1/2 of 8 minus, and then antibonding is 2, 4. So 1/2 of 4 is equal to 2. So that's where we get the O double bond O. And so we see that's a stronger bond. Okay. If we decide to go O2 plus, then we can see that actually we get rid of all of the, let's see if we do this. So if we get rid of, make O2 plus, sorry, 2 plus, then O2, 2 plus, the bond order is 1/2. We still have 8 bonding and 0. Oh, sorry, just 2 antibonding. 2 antibonding. Right, because the only antibonding we have is the sigma 2s. So this actually has a bond order of 3. Okay, so that would be O. Okay, and that would be a 2 plus charge. Now, does that mean that's going to be the strongest or most stable? Stronger interaction, more overlap, but not overlap, but it's a stronger interaction by bond order, but not necessarily means it's most stable because of its charge. So anyway, that is another example of a MO diagram for a molecule. We'll only be doing homogeneous diatomic, which means 2 atoms that are the same. You can do different ones, and that's totally fine if I give you the MO diagram, because you're just putting in valence electrons, putting them into the MO diagram, and then analyzing it. I guess we could say that both cases, when we had all the electrons, which I'll put back, nope. That this was so if we go here, it's going to be paramagnetic, because if we go here, it's diamagnetic because there's no unpaired electrons. It would have a bond order, we said that, and then the HOMO would be this 2 sigma 2 pi 2p, and the LUMO would be sigma 2p star, and that's all you need to be able to do to describe that. So that is molecular orbitals.